Now, coming out of states of matter, we want to take a little bit of time to look at gases more specifically, just because their properties are different. They behave differently. And and there are things that are always present, but we can't see, like I just kind of talked about. So there are properties of gases, and most of these properties are related back to the kinetic theory of matter. And first property, and this is one of the ones that people tend to struggle with the most, is that gases have mass. The air in the room has mass. This is why wind has force. Because if there's no mass, there's no force. That's why when you feel wind blow against you or against something, it has to have some kind of mass to it in order to have a force to it. But really the easiest thing to do here is if you have a decent scale, is you weigh an empty balloon, blow it up, and then weigh it again. And the balloon that you just blew up, the only difference is the air that you just put into it. And it will now weigh more because the air has mass. And so that's the simplest, easiest way to explain this one. All right, gases are easily compressible. This one's pretty common sense. Think about how much air you breathe in 30 minutes and you take all that air and you squeeze it into a scuba tank. Or one of those compressed air cans, or a propane tank, or whatever you're talking about. The idea they're compressible is pretty common sense. And this is based in this idea that gas particles are far apart with no intermolecular forces going on. And so since they're relatively far apart and they don't have any forces, you can actually squeeze them together and get them closer. You can squeeze them to such a point that they become liquids, but for the most part, we're talking about most gases, we can squeeze them a lot, 100, 1,000-fold, and they still won't become liquids. Okay. A gas will always fill its container. That's because they're in constant random motion, that when you release a gas into a room, it's always going to, through diffusion, completely fill the room evenly. Not only do they completely fill their containers, they're going to fill their containers evenly. That you're going to have kind of the same amount of gas or gas pressure in one part of the container that you are going to have in a different container or a different part of the container. All right, they diffuse the quickest of all the things. That's because they just move the fastest. And we say they're particles that when they run into each other, they don't lose any energy, therefore things go fast. They exert pressure. And pressure is, and we'll get to this in a moment, but pressure is related to kinetic energy, which is related to temperature. These correspondence between the two columns don't always correspond perfectly, but for the most part, that's where these properties come from. So then, kind of like I just said, the pressure is related to its temperature. And then not related to it, but still a postulate is that there's no intermolecular forces between gas particles. All right, so those are the things. And now, the properties are things that I would really not necessarily memorize, but make sure you know and you're familiar with. The kinetic theory stuff behind it is helpful, but not essential. All right, so one of the most important properties of gases is that they exert pressure. And we can think of gas pressures coming from two places. The first way to think about air pressure is to think of the weight of the column of air above a point. That between where you're standing now and the top of the atmosphere, there is a column of air above you, and it has a mass. And it is pushing down on you and exerting a pressure on you. Now, this pressure is equal in every direction. So it's pushing on the bottom of your hand and the top of the hand and the side of your hand all equally. And that's part of why we don't feel it so much, because it kind of cancels itself out. But a good example of this in terms of just dealing with a different fluid would be diving to the deep end of a pool. When you dive down to the bottom of a pool, all of a sudden you start feeling your ears hurting. Okay? What you're feeling is the pressure or the weight of all that water above you. From where you are at the bottom of the pool to the top of the pool, that column of water above you is pushing down on you in every direction. And the place you feel it most is on your ears. Now, water, since it's significantly more dense than air, it takes less depth of water relative to height of air to have that effect. And so that's a similar process. The other way to think about gas pressure is that it's simply the force of the particles colliding with the container. That this is what holds up a balloon. This is why a balloon blows up. When you push air into the balloon, it now begins to hit the balloon. And those particles, even though they are small, and even though they are very, very spread out, they are still running into the side of the balloon and causing it to remain blown up. And that's what's going on. That's where the pressure is coming from. The more air you put into the balloon, the more particles you have, the more force they are exerting on the balloon, therefore the bigger it gets. Okay? So this force can be related to the amount of gas you have. The more gas you have, the more collisions you're going to have, the more pressure you have. It can also be related to the kinetic energy. That the warmer the gas, the faster the gas particles are moving, the harder they're going to strike the surface. I mean, think about it. If you get hit by a tennis ball moving at 10 miles an hour versus a tennis ball moving at 100 miles an hour, there's a big difference in the amount of force hitting you. Okay? In the same way, in a container, there's a big difference between room temperature and putting a can of paint, spray paint into a fire. Because as it gets heated up in the fire, the particles start moving faster and faster and faster. They start hitting that container harder and harder and harder until the container cannot hold the pressure anymore and the can will explode. And so that's another way of thinking about pressure. All right, there are two ways to measure pressure. There's one that you're probably most familiar with, which is a barometer. This is a very crude picture of a barometer, but this is where it started with. That basically, if you have a pool of mercury, and they use mercury because it's the most dense. You can do this with other things like water, but it really gets crazy large when you're trying to deal with water. And so what they did is they were dealing with mercury, and they basically they took a vacuum tube. They basically took a tube and they sucked all the air out of the tube and inverted it into the mercury. This is important. This means there's no air pressure here. And there's nothing pushing against the mercury inside the tube. It is simply gravity, and that's it. And so what's going on is gravity's pulling down on this mercury, while the air pressure is pushing down on this, which pushes it up. And so there's a force from the air pressure that's pushing this column of mercury up. There's a force from gravity pushing it down. And where those are equal, we call that our atmospheric pressure. Okay? Normal atmospheric pressure is 760 millimeters of mercury. So from here, from the mercury level to the top of the column in the barometer, under normal conditions would be somewhere right around 760 millimeters. Or 76, we're looking at 76 centimeters, which comes out to, if I remember correctly, somewhere around 33, 35 inches of mercury. Now, mercury is 13 times more dense than water. If you did the same thing with water, instead of being, let me just round off the 36 inches to make the math easier. So that'd be 3 feet of mercury. All right, that's a lot of mercury. All right. Now, if I did it with water, because water is 13 times less dense, the column would be not 3 feet, it would be 39 feet, 13 times taller. That's why we don't make barometers out of water, because nobody wants a 40-foot column of water. Can you imagine trying to make a 40-foot column or something to hold water that's 40 feet tall, and you're trying to read it? That's just not very practical. So having something that's closer to 3 feet is a lot more practical, and that's why we use mercury for barometers. The second way to measure pressure is what's called a manometer. And a manometer is a relative measurement. It's used a lot in chemical plants and other things like that to measure pressure. And so what's going on is you have some fluid, and it could be a gas or it could be a liquid, flowing down a pipe. And they want to compare the flow rate at different places. And so they, maybe there's somewhere where it narrows or something, or some process happens in between. And they want to measure the pressure drop or the pressure change from one point to another. And so you can say this side has more pressure because it's pushing it down more, this side has less because it comes up. and you would measure the difference between these two heights, and it gives you a relative pressure, that this side is 5 millimeters of mercury more than this side, or whatever unit of pressure you happen to be using. The liquid in here can vary. A lot of times it's some type of an oil, sometimes rarely mercury, but it's something that's not going to react with whatever you're dealing with, that kind of thing. I've seen a wide variety of things. All right, so that's measuring pressure. So we know pressure is due to one of these two things. We can either talk about it in terms of kind of a hydrostatic situation, or some type of pneumostatic, I guess it would be, of the column of air above you. Or we can talk about it, and this is how we'll generally talk about it, as the force of particles colliding with the container. And then we can also measure it multiple ways, directly with a barometer, manometer for relative. We have pressure gauges that they're giving you an actual measurement, but they're generally going to be something more in terms of a relative measurement. All right, units of pressure. This is one of the things that makes gases frustrating, is there are lots of units. SI unit is Pascal. A Pascal is relatively small, and so kilopascals is more common. And so you would talk about it in thousands of pascals. Okay, so an atmosphere is another way of talking about it. If you talk to somebody who's a diver, they will talk about this, that they will relate that depth into atmospheres of pressure. You know, that once they get to a certain depth, you know, and they're like 2-3 atmospheres, then when they have to do the decompression coming back up to prevent the bends. And so that's the kind of thing that's going on. Like I said, pascals are small. One normal atmospheric pressure, just what we would experience at sea level on a normal day, not too sunny, not too cloudy, it's going to have 101,325 pascals. Usually we just say 101 kilopascals, just to round that off. All right, we also have a bar. This kind of comes, people who want kind of the pascals, but want to keep it in that tens unit, so they just round it off to 100,000. So you got a slight difference between a bar and an atmosphere. A bar is just a smidge less, 1% less. But most people just talk, bars are more common in a lot of industrial settings. All right, if you've ever done your tires in America are going to be in PSI, which stands for pounds per square inch. 1 atmosphere is 14.7 PSI. All right, which is relative, just under 7,000 pascals. And then, like I said, millimeters of mercury. 760 is 1 atmosphere, and they're equal to about 133 pascals. And so that's your units of pressure. And so you can convert between these units of pressure just like we've converted between everything else. Take your given over 1, use your conversion factors, which are given here, and you convert from one unit of pressure to the other. And so that's your basic introduction to gases. Now we're going to look at how gases behave in the next lesson.